So last time we did a review on vector. Let's just quickly have a look on it. So we have u, v as vectors. We have alpha, beta as scalars. So we can do linear superposition. A equals to alpha u plus beta v, and it equals to this. So we also defined some norms for vectors, where the L1 norm is the summation of the absolute value of every element inside the vector. L2 norm is square root of the square of everything summed up. And let's do, what is the infinite norm? Yes, the largest. The infinite norm is the largest element, the absolute value of the largest, the largest absolute value of all the elements. Okay, this is what we have done last time. And okay, so you may or may not take a note on it, because I will publish this as a PDF file online on Canvas. So if you feel okay, I'm going to go to the next page. Let's call it vector 2. So today there's one thing missed last time, is the angle between two vectors. Let's suppose here we have vector u, and here we have a vector v. Yeah, u and v are two favorite letters for vectors, and theta is an angle. So angle theta between u and v. Okay. How do we calculate this? Last time, if you still remember, we have a thing called dot product. U dot v. Geometrically, u dot v can be represented in this way. U dot v equals to the length of u multiply the length of v multiply cosine theta. So here you notice that I used L2 norm, because L2 norm is really the default norm we use to measure length in our in the most of the space or group or whatever we use. But usually we just do an abbreviation. We write u dot v equals to norm of u multiply norm of v multiply cosine theta. And if we move these two terms to the left-hand side of the equation, we can get cosine theta equals to u dot v plus the multiplication of u and v norm.
So why did you switch from the second, from L2 to L1?
Well, this is just the definition we usually use.
Okay.
So actually, which norm you use depends on what kind of a space or what kind of a problem we're using, and it's about some more advanced mathematics. If you do want to know about that, take something in the real analysis or something. That will help you a lot.
Okay.
Well, but it's in the future course, not this one. Thank you. Okay, very good question. And so from here, let me ask you one question. What will happen if u and v are perpendicular to each other? What is the angle between them? 90 degrees.
Or what?
If the u and v are perpendicular to each other. So if theta equals to 90 degrees or half of pi or half of p. We have cosine theta equal to 0. Means what? U dot v equal to 0. This is a way how we determine whether two vectors are perpendicular to each other. So if their product is 0, u is perpendicular to v. But just remember one thing. In this case, u and v cannot be 0 vectors. If you multiply 0 vector to anything, it's still a 0, right? And to this point, this is all I want to share with you about vectors. And you've already seen that it's easy, and you should have already taken this in some of your previous courses, but you may or may not still remember it. And now let's move on to some more advanced topic. Yes, vector. Vector is finished, so let's do matrix. What is a matrix? A matrix is something that contains a lot of elements or numbers. Matrix. Let's give an example. This should be from the video where a equals to 1, 3, minus 2, 4. And let's get a vector. In the video, we've done such multiplication, which is 1, 3, minus 2, 4, minus 4, 1. This will equal to, so the first row multiply the first column, which is 1 multiplied minus 2 plus 3 times 1. Here we have minus 2 times minus 2 plus 4 multiply 1. Here I'm writing dot for the times sign because it saves some space and saves some energy. And the result is 1 and 8. I think this is in the video, but I'm not sure whether you can still remember it. And I'm just copying it here. Let's look at what has happened. Here A is a 2 by 2 matrix, and V is a 2 by 1 vector. The first thing is the number of rows, and the second number marks the number of columns. Same here. And here, what is the result? 2 by 1. 2 is a row number, and 1 is a column number. So here we can know that, we notice that we are multiplying a 2 by 2 matrix to a 2 by 1 vector, and the result is a 2 by 1 vector. So where do we get this 2 and where do we get this 1? First, to do a multiplication between any matrices or vectors or whatever, the column of the first thing appeared in this multiplication should equal to the row of the thing being multiplied, which means these two numbers have to be the same. And then the outer numbers determine how many rows and how many columns we will have in our final result. This is maybe one reason why we also call the dot product the inner product. And let's look at some more examples, or let's generalize it. We can multiply a m, oh sorry, this is not m by n matrix to a P by Q matrix if and only if n equals to P. So which means we can multiply M by N matrix to an N by Q matrix. Oh, sorry, this Q is not readable. I'm sorry. And so if we have a matrix operation of C equals to A multiply B, where A is a M by N matrix and B is an N by Q matrix, what's the size of our C? So A is an M by N matrix and B is an N by Q matrix. So the M and Q will determine the size of C. So C is the M by Q matrix. And each of the elements inside C can be calculated by notice we have a comma here, which means the element on the ith row and kth column in matrix A multiply the element and the kth column and the jth row in matrix B. You multiply them together, and for each k, you calculate this product. You sum up them. You just calculate the summation, and this is your new element at the ith row and ith row and jth column in your new matrix C. We can try to perform this here. So let's see. This is the I equals to 1 and j equals to 1. So this is the first row and the first column in our result C. So the first row, and so let's do I equals to 1, k equals to 1, A11 is 1 here. And what about B11? B11 is minus 2, so 1 multiplied minus 2. And then what? Let k equals to 2. So A12 is 3. We have 3 here. And then B21 is 1. So we have 1 here. That is how we did this in the calculation. Yeah. Now let's do more exercises. Yeah, this part is a review on your linear algebra, so it may be boring, but for those who has already forgot about it, this is a very good chance for you to remember everything. Let's do more practice. So at this time, our A is a 2 by 3 matrix and our B is a 3 by 2 matrix. So if we calculate C equals to AB, what is the size of C? Oh, this is 5, I guess you're asking.
-0 right above -0.5.
Yes. So it's 1, -0, negative minus 0.5, 1 minus 1 minus 3. Is it too small for you in the back rows? Can you read this? That's good, okay. So what's the size of C?
2 by 2.
Yes, 2 by 2. So let's perform what we mentioned on the last page. So C11 equals to what? equal to minus 1 multiply 1 plus 2 times minus negative 0.5 plus 2 times minus 0.5, and no, this is minus 0.5, sorry. Okay. And this equals to minus 3, and C1, 2 equals to minus 1, 1 plus 2 multiply minus 1 plus 2 times minus 3. What is this? This is minus 9. So here we've done the first two elements in the result. So you notice that I omitted this comma there. Sometimes we keep it there, sometimes we do not. It depends on how complicated your index looks like. If your index has only one letter for row index and one letter for column index, you can omit that comma. If you have a very long expression for any one of the indices, you'd probably keep the comma or you'll confuse yourself. And what about, so what is C11? C11 is the element in the new matrix C in the first row and first column, and C12 is the first row and second column. What about, do we have a third row? Do we have a third column? No, we don't. It's a 2 by 2 matrix. Then let's go to the next row. In the next row, so we multiply the second row of A to each column of B. So what is the first element in the second? So what is A21? Minus 3. Oh, this is so thin. So A21 minus 3 and B11 is 1. Then A22 is minus 2. What is B12? B21? Minus 0.5 plus A31. A23 is 1 times B31 is minus 0.5. This is how many? Minus 2.5. And then we can also get the last element. So in this way, if we just fill these numbers into the 4 positions in element C, we get our result. C11, first row, first column. C12, first row, second column. C21 is the second row, first column. And C22 is the second row, second column. That is our C equals to A times B. So we can see that although after the calculation we shrink the size of the matrix, the intermediate process is quite complicated. That's why we want something to help us do this, and that's why we will later introduce computer to do this for us. But before we leave this page, what is D? So D equals to B times A. What is the size of D? 3 by 3, yes. So what does this tell us? It means AB does not equal to BA. Yeah, because this is a 2 by 2 matrix. However, this will be 3 by 3. If two vectors or two matrices they equal to each other, first they have to be the same size. And second, the element at all the positions should equal to each other. Or in short, they should look exactly the same. If they have a different size, they are not the same. So AB doesn't equal to BA. And so let's do a practice and calculate this D equal to BA. I will give you 5 minutes. No, 5 minutes too long. Let's do it in 2 minutes. I'm going to write it here, but please try to write it down yourself. Okay, seems a lot of you have finished. Let's wait for another half a minute. So you see, these parts are the same. So this is basic structure and pattern. You will later notice, and if you can't remember, how to calculate each element is here. Cij equals to a summation of aik and bkj. And now we can substitute everything into it. Minus 4, 0, 3, 3.5, 1, minus 2. This is a 5. 9.5, 5, minus 4. And if you are not very fluent with this, please just do some practice after class, because in the midterm exam and the final exam, there will probably be 1 or 2 questions on this, especially on the first one. Because they are just some very basic operations. Okay. Now let's go to the next page. Sure. So if we look at the part I've circled, this is the So this is the first row of B, and these are each columns in A. Minus 1, minus 3 is the first column, 2, minus 2 is the second column, 2, 1 is the third column. So this is how we do matrix multiplication. We multiply one row with one column to get one number, fill in that position, we go to the next row and next column and do this something like a dot product, get another number, fill it in. So in last page we learned that AB doesn't equal to BA, and I do want to show you some special matrices. Although it is already in the video you've watched, I still want to cover them. So first, identity matrix. Let me write it down. So identity matrix means, oh sorry, I should write this down first. Means all the elements on the major diagonal is 1, and all the other elements, they're all 0. The major diagonal, so first I should be a square matrix. And in a square matrix, the major diagonal means major diagonal means where the row number and column number are the same, are identical. So we have I11 equals 1, I22 equals to 2, I33 equals to 3, I44 equals to 4. And anything like I12, I13, I54, that when our row number and column number are not the same, the element is 0. This is called identity matrix. Sometimes it's also called unit matrix. They're the same. We call them unit matrix because if you multiply 1 to any number, you get a number. If you multiply I to any matrix, you get that matrix. That's why we also call it unit number, unit matrix. And then, if the elements on the major diagonal is not 1, it is still a diagonal matrix. One example can be this is a diagonal matrix where the elements on the major diagonal are 1 and 2. Let's test this with some matrix, let's say 1, 2, 3, 4. And see what it does if we multiply this diagonal matrix to whatever matrix. What is dA? So the first element in dA is first row multiply first column. First row is 1, 0. First column is 1, 3. So it is 1 because it's 1 times 1 plus 0 times 3, so it's 1. And then what is the element on the first row and second column? It's 1, 0 multiply 2, 4. So still 1 multiply 2 and 0 times 4. So it's 2. And what about the one on the second row and the first column? Second row is 0, 2. First column in A is 1, 3. So 0 times 1 plus 2 times 3, so it's 6. What about this? It's 8. If you compare dA with A, we can see that the first row is still the same thing, but second row is 2 times that of A. And the reason is here. So if you multiply diagonal matrix to a matrix, you are stretching that matrix in each dimension. Here, if you put D on the left hand side of A, you are stretching each row with a different factor. Let's try if we put D on the other side. So the first row of A multiply the first column of D. First row is 1, 2, first column is 1, 0. So 1 times 1 plus 2 times 0 is 1. And then here, 1, 2 multiply 0, 2 is 4. 3, 4 multiply 1, 0 is 3. 3, 4 multiply 0, 2 is 8. We can see that the first row are the same, but the first column are the same. But the second column is multiplied by 2. This means that if you multiply a diagonal matrix from the right hand side to a matrix, you are going to stretch each column. Well, this may be useful when you are doing your research or study in the future, but not that important in this course because you can always do it by yourself, right? It's easy. You don't need to remember it. And then, symmetric matrix. Symmetric matrix means a matrix equal to its transpose. If you write out all the elements, it means Aij equals to Aj I, where I and J are 1, 2, 3, 4, 5, 6, 7. So since we have symmetric matrix, we can also have anti-symmetric matrix, and we usually call them skew symmetric. where A equals to minus A transpose, or minus. From here, did you notice something? Let me write it more compact. A, I, J. Did you notice something? What if I equals to J? If I equals to J, so I equals to minus I. What is I? You can find the number. If a number equals to the negative of this number, what is the number?
0.
0. So in a skew symmetric matrix, everything in the major diagonal is 0. And in some future course, you may see this kind of skew symmetric matrix. Since we still have time, I just want to mention this. So for example, if you have a vector of u equals to 1, 0, theta equals to, let's rotate it at an angle 45 degrees. The rotation matrix will look like oh, sorry, this is not a skew symmetric matrix, I'm sorry. But still, let me introduce this to you. If you multiply this R matrix to your U vector, what do you have? Let's draw it down and see whether we have rotated it successfully. So let's say our U is originally here. This is 1, 0 point. This is our coordinate system. Originally we have our U at 1, 0. And after the rotation, after we multiplied R to U, we get square root of 2 over 2, square root of 2 over 2. What is this? This angle happens to be 45 degrees, or P over 4. This is how we do rotation. Yeah. So let's go to the next page. So have you finished this? You don't need to actually. You can just download the PDF. So let's move on. We still have several minutes, and let me finish this so that most of you don't need to come next lecture or Friday. Well, you will probably not need to come on Friday, and I will tell you who doesn't need to come. Should be a lot of you. So there's very last thing I want to show you before I tell you who can just skip the next course. So we've learned that the dot product of U and V is UTV. 1, 2, 3, 4. is 1 multiply 3 plus 2 multiply 4 equals to 11. Have you ever considered what it is? So U multiply transpose of V. What will it look like? What's the size of it? U is 2 by 1, V is 2 by 1. What is V transpose? This is 1 by 2. What is the result if you multiply 2 by 1 matrix to a 1 by 2 matrix? What is the size? Yes, 2 by 2. This equals to 1, 2, and 3, 4. First row multiply the first column is 3. First row, the second column is 4. And then second row, first column, 2, 3, 6. And the second row, second column, 2, 4. It's 8. So again, you cannot simply switch the sequence of the two elements when you are doing a multiplication for vectors or matrices. Actually, vector is a kind of matrix, right? It has 1 in one of its dimensions. It's either n by 1 or 1 by n. A matrix is n by n. That's the only difference. Okay, so for you to do your homework, there shall be one question asking you to write out the matrix form of the system of linear equations. And the matrix form means AX equal to B. Let me give you an example. If you write this into this is our A matrix, or we sometimes call it the coefficient matrix. These are our unknowns, we want to solve for them. And this is the B, or the right-hand side. So this is X equal to B form. And this is called matrix form of our linear system of equations.